Power. No. Could you hear me now? Incredibile. No talks. The setting seems to be okay. Please check. Let me know if, okay. Great. Okay, so we can start. I apologize for the delay. Unfortunately, it was due to technical reasons. Not unpredictable. Okay, so let's start today's lecture. So welcome. This is the second lecture. To last lecture, we have introduced the course, the rules, the main topics. Actually, we still have to overview the applications that of a natural language processing that we are going to address in this course. So I would like to complete the review first in order to have a big picture of what are the main topics, the main applications of fundamentals of NLP that we will address, and will be also some of them will be also the main topics of the project work. So because of course in the project work we will assign you a topic, a specific work related to a topic like summarization, sentiment analysis. So you have to know what are the state of the art, what the state of the art are, what are the main architectures, how to evaluate the performance of the system. So this kind of fundamentals are needed. And then you can elaborate on a preliminary version of a work, which is not new. So you don't have to. You are not expected to implement a work from scratch. You are expected to extend, to enrich a model, to test some variants, to add more, to make the system portable to other contexts, other languages. This kind of activity. So these are called, let me say, extensions. But you will not have to reinvent something from scratch, new from scratch. So today we will start from the applications. As I sent you an email yesterday evening because today we have to stop a little bit early, so we will have a shorter break. But then we will stop a little bit early with respect to the expected end of the lecture, which is at 4. Let's recap quickly what are the key messages behind the introduction of natural language processing. So we have started saying, okay, what is the focus of natural language processing? So mainly, the focus is to elaborate some data, some textual data, in order to process, to understand natural language. So, and we have to distinguish between what we call traditional natural language processing, was mainly based on computational linguistic expert work who were in charge of modeling specific characteristics of the language within specific context and within for specific languages. So they typically address specific tasks, like, for example, defining the rules that are commonly used, for example, to give commands to annotate some legal documents or whatever. So they are very, very domain specific because they mainly rely on static models, rule-based models. What a rule-based model is? A rule-based model is something that you encode hardly according to your domain, according to the domain expert knowledge. So you know, for example, a list of words that are peculiar to a specific context, let me say finance, sport, or whatever, and try to characterize these dictionaries or these syntactic relations so that you can exploit such a domain knowledge in order to perform some automated learning. Automated means, okay, I would like to recognize which portion of the text refers to, is the subject, or refers to a geographical location, or is a not keyword which is potentially relevant for financial investors, or I want to summarize a piece of text, just highlighting or underlying the key words, the most salient words. I can do this, of course, by applying rule-based systems, and they could work if I did a good job in building my own system, and the system tries to match what is included in the model and what is and the output, the input text, and produces an output which is, of course, let me say, deterministic in terms of outcome, and it will not be able, of course, to detect something, let me say, new. It is not data driven in the sense that it's not capable of getting new correlations among textual elements. So it misses some, maybe it can miss some important textual relationships that are hidden in the data, but you have not explicitly mentioned in your rule-based model. These are the main limitations, of course, of traditional models. Conversely, deep learning, deep natural language processing, which will be, of course, the main focus of this course, will aim at tightly integrating the potential, the expression, the capabilities of artificial intelligence, deep learning architectures, and machine learning models in digging into the data, into extracting automatically those correlations that are relevant to a specific purpose. For example, I can explore the content of a document, of a textual document, whatever document is, try to understand the correlations within the text that are discriminating for example, assigning a class label, like, for example, a category, if the document belongs to category, I don't know, finance, politics, sports, or whatever. This is a typical classification problem. We already mentioned this task, which is typically called text classification or text categorization. And this is one of the NLP applications that we are going to address in this course. Actually, it's not new for you, or at least for most of you, because it is an application of existing classification techniques to textual data. These are some challenges that I have already mentioned at the end of the last lecture. For example, if you have to assign labels to a text, one of the common issues when you have to cope with textual data is that you have typically many labels, not just two. You don't have to classify it as black or white or yes or no, but often you have to assign labels, for example, described in a taxonomy, so a hierarchical structure, including different categories at different levels of abstraction. And this is much more challenging because at a given level, possibly you have tens of different categories, so the likelihood of getting the right category is relatively low. Okay, so it's a potentially challenging, complex classification task. In many cases, you are not expected to assign a single category, as in the ticket management case that I mentioned before. You are expected to, you potentially have to assign more than one category. So it's multi-class. So you have to pay attention to peculiar text correlations that are related to different labels, and often in the training data, that you use to build your classification model, you have samples belonging to different classes, but they are often unbalanced. So this is, of course, a common problem in machine learning, not only in text mining, but it is very, very, very common even in NLP applications, because maybe you have tickets that are related, for example, to, for example, connectivity issues or hardware faults or some other kinds of common challenges, common stuff that are commonly mentioned in internal ticket, in a customer ticket, but there are potentially some exceptions that are really very rare, but may come, and you have the system is not has not sufficient training data to learn how to correctly classify them. So this is a common problem. We have to study in this course what are the solutions that are most effective for classifying textual data, which have different distributions, different characteristics with respect to other kinds of data, like tabular data, time series, images, or whatever. Moving to the other applications, I've already mentioned the case of sentiment analysis, which means trying to predict what is the opinion of the writer. For example, if you are analyzing the guest reviews for an hotel, or the sentiment, the feeling of the writer, like if it is happy or sad or angry, if it is hate speech, if it is misogyny, if you detect the misogyny. So these are different tasks that are, of course, potentially need to be addressed using different models. Maybe have peculiar characteristics, but they all belong to the category of semantic analysis. We have already mentioned, I recall the case of aspect-based sentiment analysis, which is a sub-case of this, aiming at specializing the problem of sentiment detection according to different aspects. For example, the sentiment of a hotel guest can be positive regarding the cleaning service, but can be negative regarding the food. And these aspects could be explicitly mentioned in the same piece of text. So since the text can be, for example, a paragraph, a free text comment, you have to process the text, the portions of the text that refer to different aspects, and then assign a separate score for each aspect. Maybe also, here the problem can be also that maybe in some cases, not all the aspects are covered. Because, for example, in my review, I can mention cleaning service, food, but I'm not interested in entertainment services like, I don't know, gym, swimming pool. But another customer who comes later, the week after, may be more interested in entertainment than in food. Maybe it's according to different. You don't know in advance in many cases which are the classes that are the aspects that are actually mentioned. So in order to detect the the aspects that are relevant, you can combine sentiment analysis models with topic detection models. Topic detection is another application which can be, of course, related to, but not the same. And the goal of topic detection is to describe a collection of a single document, or most often a collection of documents, in order to provide to domain end users with a description of the most relevant topics covered in the collection. Here is the slide. You want to characterize which are the main aspects covered by a document. Typically, it's not singular view, but it's a longer piece of text or a more structured document. For example, you can also analyze some multimedia content like slides or scientific papers. You want to know which are the aspects, the topics that are most relevant, for example, for indexing purposes, for summarization purposes, or even for detecting the sentiment of the writer according to different aspects. These kind of models can work at the level of single words, like, for example, a word cloud. In a word cloud, you just simply represent topics as single words, and the more frequent the word is, the word occurs in the source document, the more relevant it is. It is, of course, an oversimplification of the topic modeling problem, but this is extremely simple. It's not computationally expensive, so it's a very, very quick way to do topic modeling. Of course, can we do better? Of course, yes. There are different solutions, including models based on matrix factorization, based on probabilistic models like LSA, LDA. We will try to overview the topic modeling, the main topic modeling approaches next lecture. So next lecture will be devoted to topic modeling. I will introduce the most established approaches to topic modeling. And then during the first lab, which will be scheduled, is scheduled on next week, next Wednesday, so I'm right, or Thursday, sorry. You will also apply some existing topic modeling algorithms to real data. So this will be the topic of next lecture. This is one important thing. This problem is typically unsupervised, so you're not expected to know what the topics are, how many and what the topics are. This is typically unsupervised, or in some cases, the most likely ones, is semi-supervised. So you have some few examples of topics and topic descriptions, but not enough to build a supervised model. Conversely, in the sentiment analysis task, you are expected to know, at least for a bench, for a subset of users of textual documents, the sentiment. So it is typically addressed as a supervised problem. Okay, it is not mandatory, but it's quite common, the most common way to approach sentiment analysis. Since topic modeling focuses on describing your data by providing giving an insight into different topics covered in the documents, it is also instrumental for next steps like visualization or retrieval. So if I'm capable of detecting and describing the topics covered by a document, or for example by a web page, I'm also able to visualize the content in a smart way. For example, if you Google something, for example, if you Google the name of a famous person, or like, I don't know, President Obama, the former US President Obama, Google will return, in many cases, it returns not simply the link to the most relevant web pages, but also a short description. The description of the entity, we will call it entity, which is because it is a famous name, a recognized entity, which is a famous person, also contains a brief description. Let's try together, just to have an example. The description reflects different aspects, which are mainly the topics detected by the information retrieval system. Let's try Barack Obama. Then I share the screen also for body. Okay, like this. Here is not in English. I can try to switch to English. Thank you. Okay, I'm sorry, because here, what is interesting here is this. It collects some information, which is a description of what we will call later on in this course entity. And if you are, these are punctual information. This is not exactly what we would like to find, because these are punctual information like what is the name of the vice president, what is the date of enrollment for a given role, the title, if he has a master degree or PhD. These are punctual information. If you will have more verbose description, or at least a list of keywords, they can be extracted using topic modeling approaches. So you get, basically it gets all the web pages that are related to Barack Obama and tries to apply topic modeling in order to extract, for example, words like, for example, in the word cloud, or even sentences or combinations of words. Okay, so the description of the topic can be at word level or combinations of words, like we will call them anagrams, or even sentences. So, and of course, it depends on the type of visualization you would like to achieve. Then, moving to the next application, summarization aims at providing end users with a concise description of a verbose piece of text, like a long document or a technical report, a scientific paper, or a set of documents like a bunch of news articles related to the same event and published by different online newspapers. Each newspaper, of course, may focus on specific aspects of the event, of the news, and may highlight some relevant aspects that are maybe some of them are in common with the other news published by other newspapers, but other are different, and you would like to highlight what is relevant, not simply what is most frequent, but also what is actually relevant according to some metrics of relevance and redundancy. So the two main goals of summarization is to produce a digest, an abstract, which is highly relevant in terms of content, but also minimally redundant, because you don't want to repeat something many times. You want something that is as much concise as possible. And these kind of approaches can be addressed in different. This problem can be reformulated in different ways. So you can extract simply something that is already existing from the document, like for example, I extract some sentences, I highlight some sentences within a long piece of text, and in this way you are just summarizing by putting together some highlighted portions of the text. But of course, the selection, the extraction is not is readable only at the level of, for example, sentences. Not the entire document the entire summary is not consistent, because maybe you pick the first sentence in the document, the last one, and the one in between, and they are not necessarily correlated with each other. There are also other approaches called abstractive summarizer. Abstractive means you generate new text. You produce a new text. Of course, the new text, the output text, is not simply a rephrase of the original one, because your goal is to summarize, but is also a concise rephrase of the original one. So the goal is to produce a summary which is not exactly a composition of existing content, but is something new. So you combine words in order to form a new piece of text, new sentences, and you can do it using deep learning architectures. We will see, we try to apply some state-of-the-art abstractive approaches as well. So we will, in this course, we will introduce both extractive and abstractive models. What are the goals of these techniques? The goal is to the most common goal is to provide, to build, for example, some synthetic view of more complex content curation platforms. Like, for example, if you want to build your own personalized newspaper, you're not interested in whatever kind of news event. You are interested in specific news, like, for example, news related to Juventus, news related to Real Madrid, news related to Ukraine war. Okay, you specify the topic you are interested in, and you build your own personalized newspaper, which shows you the latest news on that topic, but not the entire news, but only a synthesized version. Okay, this is a typical case of content curation, where you adapt the content to the needs of the end user. Okay, and another very popular application is accessibility. For example, for people who have no or a limited internet connection, if I have to transmit a huge volume of data, like, for example, tens or hundreds or thousands of documents, or maybe with multimedia content like images and videos, this can be critical. For example, for e-learning purposes, for learning activities, for teaching activities, if you have to share some contents, some verbose contents with some high volume of documents, this can be critical. You can share at least a digest, a summary, which is more easy to share, and is also easy to visualize. For example, if you have some devices with limited size, or on the screen, you can put just a digest instead of browsing the entire content. So it fits some devices, some alternative devices, or some context in which you have no high accessibility for the resources. Another important aspect that we will address is also the language, because you have to summarize typically documents. The most common case is to summarize documents written in English, for example, for scientific papers, news. But it is not so uncommon to summarize documents that are a mix of documents written in different languages. So how to combine the information written in different languages? there are systems that are capable of generating summaries, separate summaries per language, or a combined version of the summary in a target language. These are called, the latter are called cross-lingual summarizers. And we will see how to address this issue. So, in a nutshell, there are many different technical aspects that need to be addressed in order to solve this problem, which seems easy, but in practice, it has many different issues and technical aspects that are relevant to address. Okay. Any questions until now? Okay, so this concludes the broad overview of the applications, but of course these are not this is not exhaustive. For example, we have mentioned at the last lecture, I have mentioned the question answering problem, which is a system that is capable of processing a question posed in natural language and looks for pertinent answer, tries to answer to the question in natural language by also retrieving the content that is relevant to build the answer. This opens, of course, this leaves room to a number of different applications. For example, conversational agents like chatbots, which are applied in a variety of different scenarios, like for example for providing remote assistance, for medical applications, for building chatbots like I don't know, Siri or Alexa, so these kind of devices. So there are aspects that are not only related to NLP, but also related to other domains, which are, for example, processing speech, which can be the speech, the audio content can be transformed into text in order to make it analyzable using the NLP techniques. So you can collect the speech content, transform it into using a so-called audio transcription phase, produce a transcripted version of the audio speech in a textual version, and then process it using whatever technique you like, for example, summarization, question answering, topic modeling. But then what is different, what changes, is actually the quality of the input, which is, of course, not the same as in the case of originally written and written text. The lack of punctuation, because the text has no punctuation. And there are also some features that can be derived directly from the audio stream, like, for example, the tone of voice, which are neglected, which are not available when you apply a classical NLP pipeline. So when you process text directly, you have other information, but you miss some properties of for example, video or audio that could be relevant to solve challenges like question answering or summarization or topic modeling. Okay. So now let's start to introduce some NLP fundamentals. So what we need in order to start playing with textual data is some theoretical notions. So today I will introduce the notation first. So some terminology that we need, of course, in order to avoid ambiguity, avoid misunderstandings. And then we will introduce the preprocessing part. The preprocessing part is very important and is also part of the classical data science pipeline. So in the course of data science, you have seen the classical steps of preprocessing, which precede the main algorithms, like the main techniques like clustering, classification, or associational mining. So there are steps like, for example, discretization, normalization, or missing value detection, which are established. So all data analysts should know are every day when you have to cope with a new data set, you typically have to spend a lot of time doing data preprocessing, because data are often noisy, are not clean, include relevant redundant part, noisy parts, are not that do not fit the data format that is required to run the machine learning algorithms. So you have to spend a lot of time, probably in the worst case more than half of your time, expected time of work for the entire pipeline to prepare data. So the majority of the time you spend in a data science pipeline is devoted to preprocessing, which is a little bit surprising, because when you start studying data science, machine learning, artificial intelligence, you would expect to play with neural networks, to set up some complex deep learning architecture, to test the hyperparameters. These are, of course, activities you will have to do, but this is not the first step, and not the second one, neither the first. It's a subsequent step. You first must make sure that the quality of the data you are going to analyze is sufficient, because the most famous claim is garbage in, garbage out. So you must be sure must make sure that what is coming into the network, for example, if you apply some deep learning technique, is suitable for getting reliable results. Otherwise, what you achieve is not reliable at all, is not effective, is not predictable. So we do the same when we have to cope with textual data. But of course, whenever you analyze, you prepare data, you must take into account the type of data you are going to process. So when you process tabular data, you have some common steps that you should already know from the previous courses. When you process textual data, there are some peculiar preparation steps that are needed. So today we will focus on the most peculiar steps, data preparation steps related to text. They mostly belong to the traditional NLP pipeline. So they are not necessarily related to deep learning. So they are commonly applied, even not really relatively new, because well, even when machine learning and deep learning were not so popular, they still have the problem to clean data. So there are some established data preparation steps that are needed in any case, whatever algorithm you want to apply. And we must know, and we must also do practice. So the first lab will be focused on this activity, which is not a secondary activity. So you must care about this, and also in the practical activities, in the project activity, you must pay attention to these aspects, because they are crucial also for achieving good results in the next analytical steps. Okay, let's start from the beginning. So what comes into as an input, I have a raw text, a raw piece of text. I have to split the textual content into parts that can be analyzed separately or alternatively, you can analyze them separately, independently of each other, or you can analyze them as a sequence. For example, one word precedes another one. Okay, so you have a structure, and we have to decide, to agree on which is the textual unit that is worth considering. Okay, so if I have a piece of text, I have to decide at which level of abstraction I want to analyze that piece of text. Because, for example, if I look at the word level correlations among textual units, I can detect some relevant information. For example, I can study the frequency of the frequency of the single words in the text, but I may miss some high-level expressions, like, for example, multi-word forms. For example, the natural language processing is not simply a combination or a sequence of 3 words in a row, but is called multi-word form. It's a sequence of 3 words in a row that globally have a specific meaning. So in order to capture the semantic behind the text, I should not only focus on the single words, natural language and processing, but I have to also analyze the text at a higher level of abstraction. Okay, this is a very, very important step, because if you miss information at the right abstraction level, you are not able, whatever kind of algorithm you apply next, you will miss relevant information. And then, of course, as mentioned here, you have to care about the language, because according to the language, you have to apply different ad hoc preprocessing steps. For example, there are languages like Chinese who have some peculiar characteristics, even in the way you formulate, you compose your sentences. And of course, the concept of word in Chinese is not the same as in English or the same as in Italian. So the structure, the syntax of the text, the use of prepositions, of articles, of verbs, is completely different. So we must be aware of these properties in order to clean the data and process it in a proper way. Okay, so if I have to split the text into parts, which is the smallest part I can consider? Of course, the single character. The single character is it can be, for example, a letter, a digit, or even a space. But does it convey sufficient information? It depends. Actually, if you have to, for example, if you have to separate different words or different sentences or different paragraphs, you may consider character level separators. For example, if you have to detect punctuation marks like full stop, question mark, in order to do it, you have to properly to analyze text at the character level. But in many other cases, splitting text at the character level is not sufficient, because you miss relevant information. So there are cases where this kind of level of detail is relevant. For example, if I find a question mark, I can deduce that the text is in interrogative form, or I can deduce that it is very likely to the sentence is very likely to end. So I can split and consider the next character as the starting point of a new sentence. But most commonly, when you have to address most of the problems, the NLP problems that we will address in this course, you have to do a step behind and consider a higher level aggregation, not simply a single character. So the most common case is to analyze text at the word level. Okay. So a word is a series of letters separated by spaces, and it is commonly defined as a smallest unit of a text, of a piece of text that may convey relevant meaning. May, because in some cases it's not sufficient. So if I have, if I analyze, if in my text I see machine and learning have specific meanings, but the combination of the two, which is again a multiple form, have a particular meaning which I would need to consider. So we must agree with the language. We must decide whether the approximation of focusing on single words only could be acceptable or not. Okay, I know in advance that I lose something, I lose some information. I have to wonder whether it is this simplification is acceptable or not. And this choice is always a compromise, a trade-off between complexity and efficiency and effectiveness. So your model will become simpler, more efficient potentially, because it takes you consider a smaller number of units, so it's the problem complexity gets lower. But on the other hand, you will miss potentially relevant information. So which is the best compromise? The answer is not unique. It depends on the application. If you want to do a step behind, you can move to the n-grams. What an n-gram is, it is a contiguous sequence of n textual units, typical n words in a row. It is important that these kind of words, these units, are considered the order matters. In n-gram, for example, n is a number, like b-gram is n equal to 2. So it's a sequence of 2 words in a row. A 3-gram is a sequence of 3 words in a row, and so on and so forth. In a b-gram, the order of appearance of the word matters. So machine learning and learning machine are 2 different n-grams, are 2 different b-grams. B-grams stands for n-gram with n equal to 2. 3-gram is n-gram with n equal to 3, and so on and so forth. The units actually can be also phonemes if you are processing transcripted data, transcription of audio speech. So whatever kind, we can agree on the meaning of a unit, of a textual unit, and then I compose the n-gram as a sequence of n units in a row. In theory, I can also compose my n-gram using entire sentences. 2 sentences in a row may be an n-gram, okay? This is not, it is quite uncommon actually, but it can be, theoretically it can be. A multi-word expression is a particular case of n-gram which conveys a relevant meaning. Not all the n-grams have a specific meaning. So if I compose machine and learning, the combination machine and then learning is a multi-word form and has a peculiar meaning. But if I compose other 2 words randomly, I may produce some not relevant, not meaningless. I may yield in meaningless combinations. A sentence is instead an entire piece of text separated from another piece of text preceding or subsequent by punctuation. Like, for example, full stop, semicolon, exclamation mark. Of course, I need to agree on which sentence separators should I consider. For example, the comma is a sentence separator. Typically not, but it can be. So you can customize your system in order to define which sentence separator it should use. Then within the sentence, you can also extract some relevant portions of a sentence, which are more. It is more complex to extract them because it's not so easy. You can use, for example, some punctuation separator like comma, but it's not always the case. Like the phrase and the clause. So the phrase is a part of sentence consisting of a group of words without subject and verb. So it's like after dinner or waiting for the bus. It's not a complete expression because it does not convey a complete thought. Whereas the clause is a part of sentence which includes also both. It is mandatory that it includes both subject and predicate. Okay. So it can be considered not a part of a sentence, but a sentence itself. But it's not because maybe the writer is elaborating a more complex thought, so it's composing a sentence which is more elaborated, which includes maybe phrases and clauses. Okay, these are subparts of a sentence. But you can extract a clause, which can be a sentence itself because it includes subject and predicate, whereas the clause is not cannot be considered as a separate sentence because it misses some key elements. Here is an example. This is a sentence where you have some unigrams, which are in practice, in this case, unigrams means n-gram when n equal to 1, and unigrams are actually words in this case, because the unit here is a word, but it is not always the case. Okay, lexical chains are actually a more complex version of sequences of words like this, which are mostly used by old-style computational linguistic experts because they try to derive some syntactical relationships. For example, which is the part in red that connects the first part of the sentence to the end part, in order to automatically detect, for example, the position of the verb, the position of the predicate, to what refers an adjective or an adverb. So it is more complex to build this kind of representations, which are called the lexical chains. These are actually not very used. I reported this for the sake of completeness, but it's not in practice. They are very, very rarely used in deep NLP. Then there are some variations or reformulations of the textual units that are worth considering. The first case is the stem, which is the most common one, and is basically it consists in a base form, a root form of a word, which is in common with other words, similar words. For example, if I say the word beauty and the word beautiful have something in common, have the same root, they have the same stem. Okay, the stem is the base form, but and they have a common part, which is of course it is related to some syntactical property, like for example an adjective or different inflections of a word, like plural or singular, different tense of a verb. If I say I'm going, I go, I'm gone. So they share the same base form. I can try to derive this common part, this base form, and in order to simplify the processing of the text at the next stages, I can say, okay, I can reconcile all the words that have the same root, the same base form. I can replace all the words with their base form. This simplifies the problem, the initial problem, because instead of having a space where I have a huge number of different units, because I have thousands of different words in a dictionary, I can reduce the complexity, because, for example, all the inflections of a verb will be transformed into the same unique base form. Okay? Even from a statistical viewpoint, if you look for frequent words, of course, if two words are different just because one is a singular and one is plural, if I say car and cars, I look at the frequency, I count the frequency of that word in a document. If I count, and for separate words, they are distinct units, they are distinct words, and I get two separate counts. But actually, they are the same expression. So I would like to join, to merge them, and get a unified count. Is it enough? Probably not, because as we will see later on in this course, we also have we can incur in some ambiguity due to the semantic of the text. So the same word, like cars, can have completely different meanings according to the context of use. For example, cars can be, of course, the vehicles, so like the vehicles, the means of transportation, but also a movie is also named Cars. So which one is correct? It depends on of course, on the context in which the word is used. We will see this because this will be a particular task we want to address. It's called disambiguation. But this will not the topic of today's lesson. We need to simplify the problem. This is, of course, a simplification, a preprocessing step. This is not always needed, actually. For some deep learning approaches, this will be not necessary, neither useful. But in many other more traditional approaches, this will be the standard. So you apply this simplification step before running the machine learning algorithm. How can you derive the root form of a word? So there are different ways. One is more simply, the simplest one is to truncate the word, looking at the common part. Okay, I truncate, I look for the common part, even if this approach is error prone, because for example, some inflections of the verbs have no root part in common. For example, if I say I go to the hotel or I went to the hotel, go and went are two at the same should have the same base form, but they have no common part. They have not the root part is different, actually. So the way of writing the word is different. So in order to derive such a relationship, like for example, go is related to went, I need a dictionary. I need some syntactical model. I need some domain knowledge about the language. I can do this, and this process is called lemmatization. And I derive what is called a canonical form, which is something more an enriched version of stemming. So this is not simply base form. This is again a base form, but it is, let me say, a more enhanced, a more enriched version, because I do consider expressions or even multi-word expressions. I also look at dictionaries and domain models that are capable of saying, okay, this, even if the words have not exactly some, did not share part of the sentence, they have some common characters, they refer to the same base form. Okay, so in lemmatization, you are able to discriminate between two words that are different but have the same base form, and you are also able to detect some multi-word forms like machine learning, data mining, natural language processing that are typically neglected by stemming. So when you apply stemming, a typical stemmer, maybe you the typical implementation, not announced implementations, it processes one word after the other separately. So it does not consider, does not look for multi-word forms. So if it has to process natural language processing, it extracts the stem from natural, the stem from language, and the stem from processing. Okay, then this is not, of course, the best you can do, the best option. Okay, so summarizing, the lemma is a canonical form of a word or a multi-word expression. The lexem is actually a variant, which is actually a generalization. It's not so relevant actually in our case. And the stem is a base form, which is the most commonly used one, because it's easier to get. So you don't need any domain-specific dictionary in order to extract this stem. Sorry, you need no. Sorry, I said the wrong thing. You need a dictionary, but you don't need some advanced syntactical model. So you need just a raw list of root forms, and you try to do simple matching with the root form. Okay, you don't need to do advanced processing of the text, knowing, for example, the relationship between different tense of a verb, like go, went, gone. So it's a more simplified version of text transformation. I'm looking for an example here. Okay, no, here is not. Let me show you. Okay. So the lemmatization step is the process of determining a lemma of a word by deducing its intended meaning. So it's not simply cut the word taking just the root form, but trying to guess which is the intended meaning. So which is the root word that is referred to. For example, if you have many tense of a verb, many forms like go, went, gone, you try to reconduct that words to the root form, which is typically the present continuous. If you have plural, lemmatization. Instead, stemming is more simplified. I show you in a moment. If it is just a truncation of the word. Actually, typically truncation is for you get a longer form, you get a truncated version, like beautiful, beauty. I show you as an example here. Yeah. For went, it depends on what you put in the dictionary, because for the stemming approach, you just pick as an input a dictionary of words, typically a dictionary of stems. They are typically provided by the in the most common tools like Spacy. You can find a dictionary of stems, a default dictionary stem for English, one for Italian, and you have to check which is the contracted form of the word. Like for example, for went, probably it's the same because the word is very short. But if you have if you find, for example, consultant, you will cut as consultant because tries to find a root form which is the same for all the variants. Okay. So you can modify your model. So maybe I don't know exactly the case of when because it depends on what is encoded in the model. But if you don't find a stem and you need it, you can personalize your stemming model. And this is the case, especially for not for Went, because Went is not so discriminating for activities. But if you have some words, some domain-specific words, like for example, if you are analyzing financial documents, you can find words that, like I don't know, SRL, SPA, Inc., like Google Inc. These are typically words that can be very recurrent, or you have root forms that are not standard and that can be encoded. Okay, so you can enrich your model, saying, okay, these are root forms that are not general purpose, but they are domain specific. Please. Oh, yes. Both depend on the language because you have to specify, if you, for the stemmer, from the lemmatizer, you need to specify as input which is the language. You can personalize. You can create your own stemming dictionary. And of course, if you personalize, including also words of other languages, like for example, for an Italian stemmer, you can also include the stem of some few words that are in English but are very common in Italian, like so computer. Computer is a word that can, or computer computation. No, computation is in English. I don't know. Some words that are in other languages but are used also in Italian, for example. Okay, here you have some examples. For stemming, it's just a simplified version of lemmatization, where you don't really need to look for the root form, but you just truncate. Like for example, in this case, you have study, which is extracted from studies, and study with the Y, which are different stems. Of course, this is not the best you can do because they have some related meaning. So what you want to do in the best case, in the best word, you have to reconduct both cases to the same lemma. But in the case of stemming, it may happen that you have related words that are considered as different stems. Okay, so it's not perfect, but it's just a very fast and efficient way to deduce some simplified versions of the text, to reduce the cardinality actually of the candidate items. Because the problem is that the text, the vocabularies of the dictionary of Italian or dictionary English includes thousands and thousands of words. So the problem of processing a larger document corpora can be very extremely challenging, because the complexity, the order of complexity in terms of the problem depends, of course, on the number of occurring words. And if you are able to simplify it, you may you're likely to get a more tractable version of your data, which of course loses some semantic relation, some semantic expression, some semantic meaning, but still retain some relevant correlations to your purposes. So you have lower computational complexity, approximated results. You have to decide whether it is acceptable or not. In some cases, especially for state-of-the-art architecture like transformers or similar, this is not recommended. You don't need to do so. In other cases, like applications for more traditional applications of machine learning to sentiment analysis, you typically do stemming and then apply the classifier. Okay? So it depends on the case. Of course, knowing whether it is appropriate or not to apply these steps like lemmatization or stemming, we will see now other steps like stopword removal, tokenization. This is an ability that will be required for this. We would like to teach in this course. So you, at the end of this course, you should be able to discriminate between different modules and to properly set up this kind of preprocessing step according to the goal you want to achieve. So it's not always do stemming because it's simpler, or always do lemmatization because it's more informative. Apply this and this and this in this order. It depends on the application. It depends on what you have to do. It depends on the problem statement and the architecture you choose. Yeah, of course. Because if you apply, yes, it's not possible. You may try to, it doesn't make sense actually to do both. There are some lemmatization tools that are also context dependent. So try to detect what is the intended meaning of a word, also looking at the context, but they are very extremely computationally intensive and not sufficient because you need some domain-specific, language-specific models, which are not available for many languages and for many contexts. So if you work on a social network, it is very difficult to find the appropriate model, lemmatization model. So at the end, you will use, unless very specific cases, you will use standard lemmatizers. If you can't find a suitable solution, probably you will adopt different approaches. Which don't need this. So you try to skip this step if it is so much complex to find an appropriate model. So it's too labor intensive. It's too complex to find to build your own model, because building a model for a language or even for a smaller context is extremely time consuming. So it's not worth in many cases. In many cases, you try to look for a turnaround, and you look for an alternative solution. Okay, let's go back here because we missed some steps. Okay, here you have see as an example of what I said before, so the clauses and the phrases, which are different because they are different subparts of the sentences, which either include the key elements like the subject and the predicate or not. This is by detecting actually phrases and clauses is not easy, and the complexity is similar or even worse than lemmatization, because again you have to analyze the morphological structure of the text, detect the role of each word. We will see in a moment how, and this is very computationally intensive. So don't do that unless you have a clear advantage. because it's extremely inefficient, especially if you have to analyze a big, huge collection of documents. Okay, then moving upwards, you have paragraphs, which are typically sequences of sentences together, put together, and then these paragraphs can be combined in a section. Sectioning is a very powerful way to divide text and to make a complex NLP task simpler. For example, if I have to process technical reports or scientific papers, so documents coming from a scientific domain, so technical domains, they are likely to have a common structure, likely have an abstract, have an experimental part, have a methodological part. If you are able to find some recurrent properties of the text in terms of structure, you can split the problems, so simplify the problem by processing each section separately, or alternatively, if need be, you can look for specific aspects, specific text correlations within specific section, because you do know, you can leverage your a priori knowledge of the structure of the text, and even you can leverage the meaning, the expected meaning of a section. For example, if I have to summarize the main empirical achievements of a study, of a scientific study, it is very unlikely to find it in the related work section, because in the scientific paper, related work means look at what are the prior works, what they did, but don't report empirical findings, achievements. The achievements are in the section experiments, okay? Or if you wanted to have a digest of the paper without applying any further text processing analysis, pick the abstract or the conclusions. Okay, this is an a priori knowledge. So this is not, unfortunately, in some cases, in some scenarios, you don't have any structural information. Sectioning is not available. For example, if you analyze tweets are so short, have no structure, because typically are 100 and I don't remember, 140 or even more, something more now. Recently they have extended, but they are very short pieces of text. So no structure, no further information. But if you have to analyze longer pieces of text, it is likely to, it is convenient to find some recurrent properties in the text which allow you to simplify the problem. Either you can analyze text within different sections separately and then combine the information. For example, for text summarization, you can summarize each section separately and then try to put together the information coming from different sections. Or you can target the search, the retrieval of the content based on your a priori knowledge of the structure of the text. For example, if you want to index the web pages, you know in advance that the HTML code is tagged, and the tags can be used for sectioning the page. The tags are annotate the text, providing some information about even the relevance of the content. Like, for example, H1 is an HTML tag that tells you that it is an header of type 1, of level 1, so it's main title. Header 2 is a title but of level number 2, and so on and so forth. So this is worth considering if you are processing web pages, because you have an indirect information about which part of the text should be considered first, or which part is a synthetic version of another one. So in order to capture some potentially redundant overlaps or redundancies in the text. So sectioning means divide text, long pieces of text, typically into parts, which can be paragraphs, subparagraphs, sections, and leverage such an information in order to address classification, summarization, question answering, and so on and so forth. So this information will be instrumental for more efficiently addressing and more effectively addressing specific tasks. Okay, here you have a more complex, more complete taxonomy of the preprocessing steps. Actually, we will mention the main one. You can, of course, if you are interested in, you can go deep into add the remaining ones. Some of them are a little bit less used in recent applications, so I don't explicitly mention, but of course, if you want further information, I can provide you, of course. I would like to mention the most relevant ones. So the most, let me say, common steps of cleaning, of text preparation are cleaning, tokenization, stopword removal, part of speech tagging, and stemming lemmatization. Actually, I jumped to this because I would like to show you the examples. So I moved. We already seen what is the expected result of this. Now we have to see what means processing the text for cleaning, for tokenization, for stopword elimination, and for part of speech tagging. Okay, so we have to address the other steps. I think we can take a short break now, and then we'll start. Could you hear me? Thank you. Okay. Let's restart the lecture. Sorry, I apologize to have a very short break because we have to finish a little bit earlier, so I need to summarize. Okay. Next time we will have a longer break and stop as usual at 4. So just an exception. Okay. What we want to do now is to enumerate the key preprocessing steps, which include also lemming and stemmatization, which we already mentioned before. But there are also a number of other preprocessing steps that are instrumental for doing further advanced analysis, including deep learning model training and fine-tuning. These are not mandatory steps. These are common steps. They need to be properly selected, adapted, and configured according to your purposes. So don't take this list as the list of ingredients that you have to put in every NLP pipeline, which is definitely not true. It is a set of possible choices, popular choices, which are useful for handling different types of data. Of course, one of the practical activities we will do, especially in class, even as exam simulation, is to solve some practical tasks. So I will assign you a problem. I tell you, okay, if you have to solve this problem, which procedure you should design. Let's try to design your solution, your own solution. And of course, some of the preparation steps include these cleaning and preprocessing steps. So let's start from the beginning. Cleaning means filtering out noise, filtering out redundancy. If you know in advance that some portions of the text are not relevant to your purposes, you are, of course, it is more convenient to filter it out, to remove whatever is potentially noisy, because even especially in a deep learning paradigm, you have during the training phase, you try to let the network learn from itself what is potentially relevant. So in order to avoid introducing a bias or noise in network learning, it would be more advisable to clean data first, especially for the parts or the portion of the text that are for sure not relevant to your purposes. So let's show you the steps. Of course, at the level of charters, which is the title level of aggregation of the text, you can remove some unrecognized characters or some special characters that are not that cannot be processed by any further subsequent step of NLP. For example, if you get the text from images with OCR or similar technologies, it is likely to incur in errors in the detection of the text, in the generation of the text. So if the system was not able to recognize a given character or symbol, it is more visible to remove it or to replace it if you are confident what you are doing. So what are the most likely candidates to substitute it. So you have to remove or replace, if appropriate, redundant characters, unknown characters, or special characters, because of course they could lower the quality of the outcome. Then there is a step which is quite common in NLP, not always mandatory, because we will see that there are approaches that try to that work even in scenarios that mix uppercase and lowercase. And this step is called normalization, which means transforming the text into lowercase or uppercase. Okay, so if you have a mix of lowercase and uppercase, you can make the whole text uniform, which is good in some cases, because a word that has composed of a sequence of characters, some of them are uppercase, some other are lowercase, could be deemed as different, could be different from another one which is, for example, lowercase. But this is also bad in some cases, because, for example, if you want to recognize the names of the persons, it would be helpful to look at words that start with an uppercase, because of course it is a superset of the proper names of a person. So it depends on the case. It is a possibility. There are tools that do it automatically, a very simple step. This is a case normalization. No, don't confuse it with a normalization step typical for data science, for numerical variables. Normalization for a numerical variable is a completely different meaning, where you have a variable like, for example, temperature. You want to reconduce the range of variation of that temperature values to a fixed range, like 0 and 1. And this is called normalization. Here is case normalization. Okay, don't confuse, because the name is similar, but the meaning is completely different. Then format conversion. Okay, here is what you need to take into account the sectioning, and not only the sectioning but also the structure, because maybe within the section you have also some more punctual information, like, for example, within a web page, if you look at the source HTML code, not only you find the sectioning, so the division in paragraphs, subsections, first title, second title, but also some highlights. Like if I put a word in boldface or in italic, this can be detected by simply parsing the HTML code, because you have an opening tag, an end tag, and you can indirectly deduce that word has a particular meaning. For example, if you want to detect the most salient topics, these words must be potentially considered as more relevant than other. So date format conversion means transform the data in a format that is suitable for the next steps, but paying attention to avoid wasting potentially relevant information. So maybe some of the information about the schema or about the structure is potentially relevant. So you are not sure, or maybe if you know it in advance, okay, do consider it, do model it in a proper way. If you don't know, keep it, of course. If you are sure, you have to make sure that this is useless. In this case, you can disregard. But in most cases, these are the formats you find, like a text in HTML, in XML, in JSON or CSV. In some cases, you have a standard form like HTML. You know the meaning from the standard of the language. In other cases, which are not always the case, you also have a schema. The schema means an explanation of the meaning of the tags, and even a style, so you know how to use that tag. You know that, for example, /b is the closing tag of a boldface express string, which starts with the end tag /b. The tag b is an opening tag, the tag /b is closing. This is the syntax of the language. And you can have a schema which is used to annotate whatever kind of documents. Like most common way to annotate documents is nowadays is JSON format. So if you are familiar with this kind of data formats, you can leverage the information hidden in the metadata, so the data described in the data, in order to improve the quality of your natural language understanding process. So metadata are worth, in most cases, in order to pick the portion of the text that is relevant. For example, here you can consider the body and disregard the header, or extract some relevant information from the header, or for parts of the header, or consider some highlights in the text, or some numbering, some enumerations. You're welcome. To remove all the metadata? Whether to remove or to consider by doing feature engineering. So what we will do next, I have not described it in depth, is to define some features that describe the text. The description of the feature, so the transformation from the raw text to a feature representation, is called feature engineering, and is also common to other data science applications, not only text. In text, you have two ways, basically. You can explicitly decide which are the features that are relevant to your purposes. For example, you may derive them from the structure, from the sectioning, or from other stuff, like, for example, the words that are most frequent, whatever. Or you can let the network learn from itself what are the features. And this is the deep learning paradigm. So if you let the network do feature engineering on itself, doing some inductive process, is deep learning. And if you apply a more traditional approach, you explicitly decide based on your a priori knowledge which are the features that are relevant, and then you apply machine learning next. Of course, which approach is the best, you don't know in advance. It depends on how many data, the amount of data you have, the a priori, the level of knowledge that you have on the data, because if you have many information, you are likely to do a good job in manual feature engineering. If you don't have enough information, better to let the network learn and hope that this works. Maybe you set up the hyperparameters on the networks, but you don't have to decide which one is relevant or not. It's also a problem of proficiency. So if you are an expert on the data you are analyzing, you can decide, okay, this is relevant, this is not. I can model this in a way that is instrumental for that purpose. If you're not an expert, maybe you make some arbitrary choices which are actually harmful. So you have to pay attention to these aspects. Now, pay attention because, no, here is not, sorry, I'm not in the right place. I'm sorry. So this slide is not in the right place. I will fix it. It should be after all the other steps. So I put it maybe as a typo. Okay, next one, tokenization. Tokenization is actually is a step that we implicitly already applied, because when you decide to work, for example, at the word level, of course you have to split text into words. If you decide to work at the n-gram level, where n is equal to 1 or n is equal to 2, you have to generate all the possible combinations. So you split the text into subunits. Of course, if you have to decide to describe your data using a feature-based representation, it is not mandatory to have a single way to text splitting. So you may consider both single words and n-grams. This is quite common. So you're not obliged to choose a fixed level of granularity. You may describe some features at the word level and some features at the sentence level or at the n-gram level. It is quite common. Of course, this choice, the tokenization step, is language dependent. It is weakly, not really strongly, it is weakly language dependent in the case of European languages, because, for example, if you take a tokenizer for English and you try to apply it to Italian, maybe it makes some mistakes, but it works quite well, because actually word separation, for example, if you are separating words or sentences, is based on punctuation. And punctuation marks in English are similar to those used in Italian, okay? So the final outcome is similar. If you move to some different languages like Russian or Chinese or Japanese, this is not the case. So you have to choose the right tokenizer according to the language. Pay attention to what the token means, because in some cases, for example, the punctuation or some special characters, numbers, are considered as separate tokens. So it depends on the implementation. You have to look at the guidelines and the specifications of the library. Here is an example of library. These kind of libraries mainly rely on regular expressions. So they try to match some rules, which are also like filters here, which are Boolean rules, like, okay, split two words if in between you find one of these symbols, like bracket or round bracket or comma or semicolon, okay? And you can also configure this system according to your own, the property of your own data. So here is an example of tokenizer. This is just an example. So there are many tokenizers. There is tokenizer in space, tokenizer in NLTK. This is from Keras, so whatever. You have, please, before doing applying any machine learning approach, please do verify that the tokenization step is correct according to your expectation. Just take a look to verify the quality from a qualitative point of view, because maybe you may incur in some unexpected error. This is very common. Stopword elimination. So we have already, before talking about stemming, we see that there are some lists of words or multi-word forms that are peculiar, that are relevant to a specific language. These words can be either the root form, the base form of some relevant words, some words that are relevant to your purposes that you want to keep not only as itself, but also keep for computing some statistics maybe. So your final your features that you put in your transformed version of the data, you have raw data in input and some transformed version of your data as output. In between, you apply some preprocessing and some feature engineering. Okay. The output of the transformed version includes features which are generated either manually or automatically by some tool, some network, some whatever. Your initial preprocessing steps must be aware of what is relevant to your purposes or not. So at the level of words, there are some words that are relevant. For example, if I have to do sentiment analysis for financial news, the word upgrade, downgrade are relevant, are surely relevant. So you must keep them. There are words that are potentially relevant, but you don't know. You keep them, and maybe you apply stemming, standard stemming algorithm using a standard list for English or for Italian or for French. And there are some domain-specific words that are particularly relevant. But also, there are also, since the natural language includes also prepositions, articles, or words that convey little semantic meaning, like, for example, conjunctions. These words are not relevant at all. Okay, so all these words, if you are sure that these are not relevant, you can delete them. Deleting them means removing something, simplifying the process, simplifying the computation, for example, of the statistics of the features. Or if you keep the words as features as themselves, having a smaller data space, so it's making the computation more efficient. This here is the output. You have a list of stop words. We call them stop words, and they are, of course, language dependent and domain dependent, because you may change the stop words according to your domain, like finance, politics, economics, or I don't know, whatever, gaming. And the output will be a subset of words that are kept. You, of course, as you can see in this picture, you have some gaps in the output. Okay, so if your algorithm has some sequential models that we will analyze during this course, must consider the sequence and the distance between the words in the sequence. This could be harmful, because here you miss some information. You have a gap here, and you don't know whether these two words are one after the other or not. So one important step, one of the most common approaches in NLP is to analyze the sequential data using a sliding window. So roughly speaking, you have a window that describe the words that are closed one after the other, okay, like this. Of course, if this window slides, you are focusing your learning process on specific words that are likely to be within the same context. So they are not they are not related to different aspects because they are very close one to the other. But if you delete the stop words, you lose information because these two words maybe are relatively distant, but after stop word elimination, they are close. Okay, so if your model do consider the distance in using this approach, this sliding window contextual approach, this stop word elimination is harmful. If instead you just computing some, for example, some frequencies, trying to highlight the words that are most frequent or that have some frequency-based properties, the order of appearance of the words in the sequence doesn't matter. Okay, do stop word elimination because it could be helpful. Okay, even because articles or conjunctions are relatively frequent. So if I if I describe the topics using keywords, and I use just a frequency-based approach, the most frequent is the most important. This could be keeping the stop words could be suboptimal because at the top of the ranking you will find the, of, so words that have little semantic meaning. They are not expressive enough because just conjunction or articles. So the absolute frequency is not a good measure of evaluation, at least if you consider all the possible words in a dictionary. So some deep learning models do not require stop word elimination, and the reason is that they need to analyze a window or consider the order of appearance of the words. So if you remove something, they lose some sequential property or related to the sequential order. There are some, of course, standard lists of stop words for many languages. For the most spoken language, you can easily find a stop word list. If you look for stop word lists for some dialects or something complex, it's not easy. So there are some context scenarios or languages or low resource languages for still there is a lack of stop words or language specific domain. Of course, there is no uniform approach. So the stop word list is not standardized. So there are some common tools, but it's definitely not a standard. So you need to customize your list to your purposes. Here is an example of list. You can copy and paste this project, and here is you can see that it includes words like he, herself, yourself, our. There are also words that you may not consider as a stop word, so you can remove if you consider them as relevant. There are also approaches that are in the middle between completely removing or keeping them, because all the words can have a weight, we can also define the features by weighting the importance of the words. So, okay, if a word has a little semantic meaning, or has a small, low relevance, you can weight, not remove, delete it completely, but you can assign a low weight. This is an alternative approach. Of course, this is not convenient from the point of view of computational efficiency, because if you keep them, the complexity of your model, the complexity of your data still remain unchanged. So let's take a look to an example. I hope you can read. It's quite small. It's not cool that ping pong is not included in Rio 2016. If you have to first apply a cleaning step. The cleaning step removes, for example, the double quote between surrounding cool, and applies case normalization. For example, Rio is transformed to a lower case. Then you apply tokenization, but tokenization is actually splitting words. So each word is a separate token, and this is not the optimal, the best option you have, because in this case, for example, some words are not should be considered as multi-word forms, like ping pong or Rio 2016. There is a step of multi-word grouping, means recognizing and generating the multi-word forms according to your domain knowledge, rule-based. These two steps are often processed together, so you don't need to find a library for tokenization and a library for multi-word. They are typically addressed. They can be addressed in a single step. So there is a unique library doing both. Okay, and you get this result, which is definitely more informative and usable than the raw text. You can, if need be, remove the stop words. Okay, it could be convenient if you have to apply some particular analytic steps. Stop words are, for example, not, that, is, okay, according to a standard stop word elimination library. And here is the result. As you can see here, these are the key elements extracted by the processing step, NLP processing step from the raw text. These can be used as features directly, or so we can use them to describe different features of the text, or indirectly, so you can, for example, compute some statistics based on for example, on the occurrences of these words. So, but this is an example, a very basic example of preprocessing, which is, I think, self-explanatory. Okay, here is another nice example, which is helpful to understand that not always preprocessing and cleaning is beneficial. For example, if I want to understand the sentiment of a claim, if I say this film was not so beautiful, was not beautiful, was not noisy or very noisy, some words, some adjectives or negations are crucial for understanding the right sentiment, the right opinion. If I apply stop word elimination, most, not all, most of the libraries remove not. Not is considered as a stop word by most of the libraries. Okay, and this is harmful. So you have two options. You can decide not to do stop word elimination in this case, or you can modify the collection of the input words, removing any negation or properly handling negation forms, negated forms. Okay, so in order to capture the semantics behind the text, stop word elimination could be harmful. For example, some for deep learning, doing stop word elimination is not recommended because the network tries to, as I told you, understand the semantic relationship based also on the sequential order, the neighborhood of a word in a sequence. But there are cases, there are critical, challenging tasks. For example, where the network, even deep learning networks, may encounter problems. For example, to detect sarcasm in a text. If I use sarcastic forms of expression, the ability of the network to detect a sarcastic opinion, the right opinion in a sarcastic expression is limited. Still, many of the state-of-the-art deep learning models get incur into errors because of the complexity in capturing the right portions of the text. So the problem is that here the deep learning network tries to generate the features on its own from the raw text without any explicit indication from the domain expert. And of course, in some cases, this is very challenging, it's very complex. Okay, another step which is commonly applied is called part-of-speech tagging. This is again language dependent and also context dependent. It is not so easy to find a library that fits your actual needs, because the goal here is to find the role of the words in a text. For example, I have a piece of text, like for example a request from a user to a chatbot. I want to detect which is the noun, which is the verb, which is the preposition. Okay. This indicates the role of the word in a sentence. This is called part of speech. It is simply an annotation of each token of each word. This is typically at the word level. Okay. Maybe there are some implementations working not at, but I don't think so, because most of the nouns articles are labeled at the word level. So here is the idea: article, noun, verb. The cat is set on the mat. Why is it? It could be useful. In which situations this kind of approach could be useful? Let me recall the example. You have a chatbot, okay? I have it's called utterance. Utterance is a sentence, a spoken sentence, which can be transcribed into text. So you have a written form, a textual form of a request of a user to Alexa or Siri, the device, the chatbot. I say, please, Alexa, open the door. Why should I process the text using this kind of techniques? Right. 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 The most important thing, the first thing that they consider is the verb, because the verb mainly reflects the action, and then the object, which is the property, which is typically a parameter related to the action. This is a typical case. Okay. Of course, do we need to apply part of speech tagging every time in our pipeline? No, of course, because it is not always the case. It is not always relevant. We don't have, often we don't have enough domain-specific, language-specific models, enough detailed, so we may miss information. It may introduce also errors, because if the system makes an error, so misclassify some parts of speech, you can, of course, add some noise, some errors. But in some cases, like chatbotting, it is very important. Okay, there are then some even more complex syntactical analysis. One is called syntactic parsing. It is a more sophisticated, more complex parsing of the text, which analyzes explicitly the dependencies between words in a sentence. For example, I have the verb, please Siri, open the door. The verb refers to a given object, so open is referred to door, but the sentence can be more elaborated. So if I'm talking is a speech, you can find some complex expressions. It's not immediate for a network to derive which is the object to which the verb refers, or it's not simply the detect the noun or a verb or a preposition. You must be also aware of which is the adverb and to which verb the verb refers to which if an adjective refers to a specific noun. So these are more sophisticated, more complex properties, which require a significantly high computational complexity and more sophisticated linguistic models, which are available only for a small subset of cases. So this is not always feasible. For example, this could be helpful, will be very helpful, we will see this later on in this course, to perform aspect-based sentiment analysis. Because if I am able to detect in a review or an hotel, I am able to detect the words that are mainly related to a given aspect, like cleaning services, toilets, or food, the breakfast. I can look for the dependencies among that target words and, for example, the adjectives. The food was, the breakfast, the food was delicious. Okay? Delicious is an adjective that refers to a given word. If the word is is peculiar to a given aspect of the review, I can deduce the sentiment related to a given aspect. So delicious is a word that indirectly indicates a positive sentiment, but it's not a global sentiment. It's a sentiment related to that specific aspect. How can I map that relationship between the sentiment of the adjective and the specific aspect using, for example, syntactic parsing? Is it clear? Any questions? Okay, there are actually some simplified versions of these models because, as I told you many times, linguistic models are very nice, are very powerful, but are almost are not applicable in most cases because they require tight description, a rich description of a given context of a given language. So it's very, very specific. But actually, this kind of relationship, for example, descriptions of part of the dependencies among words in a piece of text, are not all relevant. So we are often interested in discovering relationship dependencies among specific portions of the text, among specific kinds of words, of concepts, like, for example, locations, temporal references, specific verbs that refer to, I don't know, weather or something like that. So there are, basically, you can neglect some of the dependencies in the text by thus considering a simplified model, linguistic model, which is actually able to capture only a subset of the possible dependencies. So some of them are actually not considered. It considers only a portion of them, which are likely relevant. Okay, these are simplified versions of the syntactic parsers. They are called shallow parser. Shallow means not so sophisticated. It's simplified. It's a limited version, but it's more computationally tractable. It's more portable. Then there are some very popular tools for text processing that are called entity recognition tools. They are aimed at classifying text by labeling specific portions of the text. Within a piece of text, within a document, I can split the text into parts, but some parts of the sentence can be also denoted as text span. If this span is relevant, like, for example, I say the sentence is in the United States today will happen something. Okay, United States of America is a relevant text span, not only because due to syntactical properties, but because the United States of America refers to a specific country, a specific region, as a semantic property. It is called entity. Entities are relevant concepts in the real world, like persons, locations, time events, so time references, dates. Okay, so time, space, currencies. There are some standard annotations that you are automatically detected and used to annotate text. So this is not no longer referring to syntactical properties of the text, like this is a noun, this is a verb, this is an adjective related to the noun. These are syntactical properties. Now we are considering semantical properties, semantics. So what does it mean? The semantic properties are relevant because, for example, here I can understand that this 2016 is a date, Trump is a person, I don't know, Microsoft is an organization, USA is a country, Turin is a city. Okay, these are kinds of examples of annotations, and the highlighted pieces of text are called span of are also called text span. The span is a portion of the text. This is a subset of text. A span actually is an n-gram, which is highlighted because it is likely to refer to a particular entity. So it likely retain a semantic meaning. Okay, a relevant semantic meaning, like a person, location, number, currency, whatever. So here we will describe in detail these kind of techniques. So now I don't want to go into the detail. Just just very quickly, in a nutshell, this problem can be divided into two subproblems, not at least two. The first two main problems are dividing the text, highlighting the right portions of the text. So if I'm saying today in the United States of America, it happens, I have to highlight, if I want to detect, for example, countries, United States of America. So the text span, the highlighted text span, should start from United, it should end at America. So I have to detect the right one, not a longer or a shorter portion. Okay? And this is the first task, which is not trivial. The second one is to classify that span. Given the fact that you have correctly detected, assuming that you have correctly detected the span United States of America, is it a person? Is it a location? Is it a country? So you have a list of candidate entity names, and you assign automatically that category. I don't have the picture here, but we will see later on in this course. Okay, this problem, including both subproblems, span identification and span classification, is called named entity recognition. We will address it, please. Yeah. It's an error, yes. This is an example of entity recognition, which is wrong. So it is likely to contain errors. So it's not perfect, of course. It is a challenging task. So there are. It is a real example to show that the system could make errors, and you have to fix them or to apply different entity recognizers. You have to adapt your system or to improve the quality. One possible improvement is to try to add, enrich the recognition step with a disambiguation step. So provided that you have recognized the right span, which was not the case for the second line of the example in the previous slide, if you have properly recognized the span, then you have to classify. But the word can refer to different things. The same word, like for example here, Amsterdam could be a city, so a location, or could be a ship, or could be other things. So I don't know, the Amsterdam Stock Exchange or whatever. Okay, so it could refer to completely different meanings according to the context of use. So you have to look at the words surrounding and understand that, for example, if you are talking about the city, or if you are talking about a ship, or if you are talking about something else. This step is called disambiguation. And of course, this can be helpful to improve the quality of the second subtask, which is the step of span classification. So if you assign wrongly detect the span, you did a mistake. But if you are able to correctly detect the span, you can improve the quality of the span classification using some ad hoc techniques, which are aimed at detecting the sense of a word in a sentence based on the analysis of a deeper analysis of the context. So of course it's an additional computational task, which is not free. So it could be time consuming, it could be complex, but of course it could be able to detect some semantic relationships which are neglected by the entity recognition step. Okay, so we have seen the pipeline. Actually, we will go deeper into these some of these techniques because, for example, there are plenty of different solutions to address entity recognition. There are different solutions to address disambiguation, and so on and so forth. So we will spend more time, additional time later on in this course in order to understand what are the most effective solutions to solve this problem. These are still open problems because addressing entity recognition is not is challenging, especially when you are coping with particular complex data, when you have lack of domain-specific knowledge, when you are dealing with low-resource languages. So it's an interesting problem that we will address in this course. Now, for now, you are going to next lab, so the first lab. You are going to apply standard libraries, so not any sophisticated solution. You will use a standard library available in spaCy for doing some for examples of entity recognition. So you will try to play with some real data in order to apply these steps of data preprocessing, like stemming, stop-all elimination, lemmatization. You compare the outcomes. You will transform the data using, you will see the syntactic parsing result. So this kind of stuff, in order to be familiar with these tools. And then, of course, we will try to refine, to try to see what are the most sophisticated solutions that are more likely to be more effective. Okay, I think we can stop now, and then next time we will introduce the text representation. Here we will see how to represent the text by applying an explicit feature representation, and then we will move to the topic modeling part.